Hello and welcome to Honors Function. In this lecture, we're going to be looking at the limit of a sequence. Let's begin. One way to think of a sequence is to look at it as a list of ordered numbers. Okay? This, for example, would be one way to write a sequence. As you move to the right on the list, as you increase the rank of the terms, sometimes these terms are accumulating close to a given value. Sometimes they're all getting closer and closer to a given value. In this case, we would say that the limit of this sequence is that value. Okay? So suppose that all the terms are getting close to L, getting closer and closer to L. We would write that by saying that the limit of an as the term number increases, as n approach infinity, is L. That's the way we would write it. And sometimes they do not come close to a given value. It can happen in different ways. Sometimes they're getting very, very large, sometimes very, very small, and sometimes they're just jumping around. Okay, so we're going to have to look at all these different ways. Now, how do we look at the limit of a sequence? Well, we have two ways of defining a sequence. The first way is explicitly, and the second way is recursively. Okay, so the first way is in function of the rank number, and in the second way, it's in function of the term before. All right, so these are completely different ways. Therefore, we will have two ways to look at limit. Okay. This way, we already know what it is, because in this way, we're looking at the limit of a sequence defined with a function. Therefore, in this case, the limit of a sub n as n approaches infinity would be the same as the limit of f of n as n approaches infinity. Now, what is the difference between this and what we've done before, the limit of f of x as x approaches infinity? Well, this is a case that we looked at in prior unit. In this case, x was a real number. In this case that we're looking at right now, n is not a real number, n is a natural number. But then, of course, we have this very simple theorem to prove. We can prove that if the limit of f of x as x approaches infinity is equal to a limit, okay, then it's an if then. So I'm going to write that like that, okay? If a then b, then the limit of f of n as n approaches infinity is also equal to L, okay? We would have this limit right here. Actually, it's an if and only if, okay? Therefore, all the technique we have studied before for functions are applicable to sequences. Let's review these techniques by going over some examples. All right, so here is the first sequence. Now, of course, this is an explicit way of writing a sequence. an is equal to f of n with f of x equal to x plus 1 over x squared. Now, we have seen that in unit 3. Right? In unit 3, this is the limit of a rational function. We talked about asymptotes in this case, and we said that the limit as x approaches infinity of f of x, okay, this is a bottom-heavy function. Well, that limit is going to be 0. Therefore, thus, the limit as n approaches infinity of n plus 1 over n squared is also equal to 0. Okay, so we have found the limit of this sequence, of the given sequence. It is 0. If you are writing the list of this term, so you start with 2 over 1, and then the next one, if n is 2, you would have 3 over 4. The next one, if n is 3, you would have 4 over 9. Next one would be 5 over 16. The next one would be 6 over 25, and on and on and on. And all these terms would be closer and closer to 0. Okay, that's what the limit means. Please go over example 2 and 3. So what is going on right here? Well, let's write the first few terms right here. You have negative 1 over 1, so that's negative 1. The second term is if n equals 2, then it's 1 over 2. The third term is negative 1/3. The fourth term is 1/4. The fifth term is negative 1/5. And on and on and on. We understand what's going on right here. We have a sequence here. How about I draw n right here, although it's a line and I'm saying I'm drawing n, right? That doesn't make sense. So here's 1, here's 2, 3, 4, 5, 6. So here, let's draw the y-axis here, and let's make the first one 0 right here. Here's my y-axis. Let me draw 1 here, and negative 1 therefore would be somewhere here. And let's start plotting the sequence. For n equals 1, negative 1. N equals 2, 1/2. N equals 3, 1, negative 1/3. N equals 4, 1/4. And then negative 1/5. And you see what's going on, right? You're getting closer and closer to 0. Okay, these dots are coming closer and closer to 0. So that makes sense because the bottom goes to infinity and the top is either +1 or -1, depending if n is odd or even. Okay, so when you have +1 over infinity, that is 0, and -1 over infinity, that is also 0. So the limit of -1 to the n over n as n approaches infinity is 0. Please go over example 5 and 6. I'm going to do example 7. So example 7, we're looking for the limit of 1 over 2 to the n minus 1 as n approaches infinity. Well, 1 over 2 to the n minus 1, so this is the limit as n approaches infinity of 1/2 to the power of n minus 1, right? Therefore, the function f of n here is 1 over 2 to the power of n minus 1. So what are we looking at here? We're looking at the function f of x equals 1/2 to the power of x minus 1. We just finished this chapter. This is an exponential function, right? And we had that, for example, this one, the base is smaller than 1. You do graph shift 1 to the right, so you would start with 1/2 of x, and then you move 1 to the right, right? But anyway, at infinity, it is still 0, right? So basically, right now, I'm using the result from the exponential function, f of x equals a to the x. Now, if you remember, the base of an exponential function had to be positive. We said that, right? It had to be positive if x was a real number. And the reason for that is that very quickly you may have some complex output, right? For example, if you look at -4 to the 1/2, right? For example, -4 to the 1/2, that's a square root of -4. That is not real. This is 2i, so it's not a real number. Okay, so we had some issues when we took a real power if the base was negative. Here, though, we're dealing with f of n equals a to the n, and n is not a real number. N is a natural number. And a natural number does not mind a negative base, right? -4 squared is completely fine. -4 to the power of 17 is completely fine. These two things are completely defined, okay? So I'm going to apply these results from exponential function, but I am going to generalize it to any base in the case when n is a natural number. So let me record the result that we had for exponential function. F of x equals a to the x, so x was a real number right here, okay? So what was the result in this case with exponential function? Well, first of all, we did have the base positive, right? And then we had two results. I'm looking at the limit at infinity, okay? So we had limit as x approaches infinity of a to the x was infinity if a was above 1, right? Because we're dealing with something like this. And we had the limit of a to the x as x approaches infinity was 0 if a was between 1 and 0, right? Because we had something like this. So again, I'm looking at this part right here. All right. Now, because n is a natural number, we can extend this result, and actually it extends to something a little bit more general. We have that the limit of a to the n as n approach infinity is, so what is it? It is 0 if, now, a is smaller than 1. That was the case before, right? Between 0 and 1. But actually, what happened when n is a natural number? The lower bound, the 0 disappear, and it's any a between -1 and 1. Okay, any a between -1 and 1. Then if a is 1, then it's going to be 1, right? If a is 1, it's a constant function equal to 1. So if a equals 1, and the limit does not exist, dne, if a is not in the interval, so not in this right here, so it's not in -1, 1. Okay, so there are several cases right here. We could look at the case when a is above 1, and we could look at the case where a is smaller than -1, and we could look at the case where a is equal to -1. You have 3 cases here, and in here the limit would be infinity, and in these 2 cases the limit would oscillate. In this case it would be like -1 plus 1 minus 1 plus 1. In this case it would oscillate, like getting huge in both directions, plus or minus infinity. Okay, so anyway, we don't need to look at these cases. What I want you to know is that the limit of a to the n as n approach infinity is 0 only when the base is between -1 and 1, not included -1 and 1. This is a major result. You need to know it, okay? These cases here are something we can talk about in class. They are not difficult, but we're not very interested in them. If you don't have a in there, the limit will not exist except if a is 1, but again, that's a very boring case. It's 1 to the n, it's 1 no matter what, right? So you're dealing with a constant function, 1, 1, 1, 1, 1, 1. Now, of course, the limit of that is not going to be different than 1, right? All right, let's go over an example here. So I'm going to do example number 8, and you're going to do example number 9. What is -1 to the n minus 1 over 2 to the n minus 1? Well, this is pretty simple, right? I can take n minus 1 out. This is a simple rule of exponent. And so you have -1 over 2, right? So in this case, a is -1/2. And -1/2 is between 1 and -1, right? So the limit of -1 to the n minus 1 over 2 to the n minus 1 as n approach infinity is actually equal to 0. Okay, I'll let you do number 9. Let's go now over the second type of limit when the sequence is defined recursively. This is a very interesting case when the sequence is defined recursively. Let's go over it. So suppose that you are given a sequence an defined recursively, and you wonder, what is the limit? So listen up, guys. There will be a very important assumption here. We're not gonna decide if the sequence has a limit or not. Okay, we're going to assume, so all the example I will give you will assume that an has a limit. This sequence right here has a limit. This is an important assumption. Okay, this is an important assumption. How do you know if it has a limit? Well, to answer this question, we would have to develop some tools. It's not the place in this course to develop these tools. Okay, you would have to do some analysis for that. A class called analysis, real analysis. No, here we're gonna assume it has a limit. So of course, all my recursive sequence will be very specific. They will all have a limit, and I will ask you, what is the limit? So if it has a limit, we're gonna answer the question, what is the limit? Okay, if it has 1, what is the limit? Okay, so actually this is not a very difficult question to answer. We want to figure out the limit of a of n, a sub n, as n approaches infinity. Okay, so what's going to be this limit? So check it out. Do you have the equation a sub n equals f of a sub n minus 1. So what about if on both sides of this equality you apply the limit? Then you would have the limit as n approaches infinity of a sub n equals the limit as n approaches infinity of f of a sub n minus 1. Okay? Now, f will be a continuous function. I'm going into some details here that you really don't need. F will be a continuous function. Therefore, the limit on the continuous function can go inside. So the right side, I can write it as f of limit as n approaches infinity of a sub n minus 1. Now, the big assumption here is that the limit as n approaches infinity of a sub n, it exists, so let's call it L. Let's call it L. If this limit exists, it's going to be the same as the limit as n approaches infinity of a sub n minus 1, right? I mean, you're not going to change the limit by looking at this as n approaches infinity. The sequence will still approach the same real number. So, what do you have on the left side? You have L. What do you have on the right side? You have f of, and then what is that? Well, that's L. So, if this limit exists, it is solution of the equation L equals f of L. So you solve this equation and you find the limit of the sequence. Let me show you how it works. So in all of the following example, we're going to assume that the limit exists. I'm asking you to find them. So here is the first sequence. You start at 1, and an is 1 plus 1 over a sub n minus 1. Okay, so what is f of an minus 1? What is that? Well, it is 1 plus 1 over a n minus 1, right? Okay, so how do you solve the equation L equals f of L? So it is L equals, what is f of L? 1 plus 1 over L. Here we go. So let's solve this equation and we'll have the limit of the first sequence. So solve this equation, you multiply by L both sides, right? So you have L squared. I'm going to also clean it up at the same time. So minus L minus 1 equals 0. And here I'll use my quadratic formula. L equals negative b plus or minus b squared, that's 1, minus 4ac, so it's root 5, over 2. Okay? So you have two possibilities. You have 1 plus root 5 over 2, and 1 minus root 5 over 2. Haha! Which one is it? Okay? A sequence can only have one limit. So which limit is it? Look at the terms of the sequence. The first one is positive, and then you take 1 plus the reciprocal of a positive number. So this is positive no matter what n is, right? And therefore the limit has to be the positive 1. The limit has to be the positive 1. So the limit of an as n approaches infinity is, what's that here? Is, well, it is phi. It's a golden ratio. 1 plus root 5 over 2. That's a golden ratio. Here's a sequence whose limit is the golden ratio. Please do example 11. Let me do example 12. All right, here is another sequence defined recursively. So what is f of an minus 1 here? It is square root of 1 plus an minus 1. Okay, so if this sequence has a limit, what is that limit? So if it has a limit, let's call the limit L. So the limit as n approaches infinity of an, I'm going to assume it's L. Okay, I'm going to assume it's L, and I want to know what L is. So L will be the solution of L equals f of L. L is going to be the solution of that. So what do we have? We have L equals square root of 1 plus L. And this is a pretty simple equation to solve. You square both sides right here. And you have L squared minus L minus 1 equals 0. Oh, here we go again. L will be the golden ratio or the other one, right? I think the other one we call it psi. It's going to be the same, 1 plus root 5 over 2. Okay? So which one is it? Again, here, all the terms will be positive because it is a square root, and a square root is always positive. So the limit of this sequence is, again, the golden ratio. All right. Please finish all of the other examples. Thank you for watching.